Good afternoon, everyone. Welcome to our webinar on how harmonics have led to 6 power factor misconceptions. I'm Tony Hoevenaars, President and CEO of Mirus International. And this is our first time contributing to the EasyPower webinars series, and we are excited to be able to participate. Mirus International is a Canadian company that has been providing very effective solutions for the treatment of power system harmonics since our inception in 1991. With this experience, we have come to realize that there is a relative lack of understanding on how harmonics affect power factor. This has led to several power factor misconceptions, which has prompted the preparation of today's webinar. Our discussions today will include 6 of the most common power factor misconceptions resulting from the presence of harmonics. A power factor and how it relates to power parameters such as kilowatts, kVA, and kVAR, known as the power triangle. Then we will describe how harmonics generated by nonlinear loads changes power factor and its relationship with the power parameters. Using computer simulations, we will show how displacement power factor, distortion power factor, and true power factor can be determined. And then the use of power factor correction capacitors to improve power factor will be introduced, with a focus on their potential for resonance with the power system and their ineffectiveness when the low power factor is caused by harmonics. Also, to improve the utilization and efficiency of their distribution grid, utilities often apply power factor penalties. We will explain how controlling power factor during peak loading conditions provides an opportunity to reduce or eliminate these power factor penalties. Since low power factor is often caused by nonlinear load harmonics, passive harmonic filters can be very effectively utilized to improve power factor. And finally, we will discuss the effect of leading power factor and capacitive reactance on generator systems. For those trained in electrical theory, the concept of power factor is fairly simple to understand when dealing with linear loads, that is, loads that don't generate harmonics. The higher the power factor, the more work produced for a given voltage and current. The power triangle shown here, we have real power in kilowatts along the x-axis, reactive power in kVAR, either inductive or capacitive, on the y-axis. And the vector sum of these two parameters results in the apparent power in kVA. Power factor is defined as real power divided by apparent power, or kilowatts divided by kVA, and it's equal to the cosine of the displacement angle, theta. Apparent power S is also equal to the square root of real power squared plus reactive power squared, or kVA equals to square root of kilowatts squared plus kVAR squared. Power factor in these terms is commonly referred to as displacement power factor. Nonlinear or harmonic generating loads, such as rectifiers, don't typically shift the current, rather they distort it. The current harmonics generated do no useful work and therefore contribute to reactive power. The power vector relationship then becomes 3-dimensional. You can see here we still have the real power and reactive power, inductive or capacitive elements, but also there's a distortion reactive power component, which is 90 degrees out of phase with the inductive or capacitive reactance and 90 degrees out of phase with the real work. Now our apparent power is the vector sum of all 3. The real power, inductive or capacitive reactive power, and distortion reactive power. Power factor is still equal to real power divided by apparent power, but it no longer equals cos theta. Apparent power now has three components: real power squared, inductive or capacitive reactance squared, and distortion reactance squared. True power factor is then equal to the displacement power factor times the distortion power factor. And it is interesting to note that this is not a new discovery by any means, as it can be found in textbooks as early as 1939, as is noted in our reference on this slide. Unfortunately, it is not widely understood, and what is new is that we have many more harmonic generating nonlinear loads to deal with than we did in 1939. With harmonic generating nonlinear loads, power factor remains the ratio of kilowatts to kVA, but the kVA now has a harmonic kVAR component as well. True power factor is equal to displacement power factor times distortion power factor. Displacement power factor is still equal to cosine of theta. And true power factor can be calculated by taking, distortion power factor can be calculated by taking the true power factor, which is the kilowatts over kVA, divided by our displacement power factor. Distortion power factor is neither leading nor lagging. Displacement power factor determines the sign of your power factor, total power factor. For typical nonlinear loads, the displacement power factor will almost always be near unity, but distortion power factor can be very low. This table on this slide shows a typical harmonic current spectrum for a single phase to neutral nonlinear load. It could be a switch mode power supply that you might find in computer equipment or LED lighting or a similar type power electronic load that has not been power factor corrected. What we show is the fundamental component, it's 100%, and then the harmonic components as a percent of the fundamental. So here we have 70% third harmonic, 35% fifth harmonic, and so on. We can also show it as a percent of RMS, slightly different values, but same harmonic content. Total harmonic distortion, or ITHD, is the root sum square of all of the harmonic components divided by the fundamental value. So in this case, we'll take the per unit values of third harmonic at 70%, and we'll square that. Then we'll add the fifth harmonic of 35%, square it. And we sum those all up, take the square root, and then multiply by 100%, and that gives us the total harmonic distortion, in this case of 83%. We can also show the harmonics levels in a particular load by its K-factor rating. And K-factor is often used to define the ability of a transformer to handle nonlinear loading and harmonics. K-factor is determined by the sum of each harmonic magnitude squared, in current squared, times the harmonic number itself. So we've calculated these values here in this column. When we sum all those up, we end up with a factor of 9. So this particular load has a K-factor of 9. So if your power system had to deal with full load of all of this type of loading, the transformer required for that would have to have a K-factor rating of 9 in order to ensure that it doesn't overheat under fully loaded conditions. And our third relationship here is the distortion power factor. So distortion power factor, HPF, is equal to 1 divided by the square root of 1 plus the total harmonic current distortion squared. So we take this 83%, square it, add 1, take the square root, divide by 1, and we come up with a power factor of 0.77. So this particular load with this particular harmonic content has a true power factor of 0.77. In this slide, we show the relationship between waveform distortion, harmonic current spectrums, total harmonic current distortion, THID, and power factor. So the first example is a typical three-phase, six-pulse PWM variable speed drive. It's going to draw its current in pulses. We have double humps on the positive side, double humps on the negative side. This distorted current waveform contains 5th and 7th harmonics predominantly, also 11th and 13th. Total harmonic current distortion is 73%, and the power factor is 0.79 lagging. When we add an AC line reactor to that drive, that line reactor smooths out the input current waveform somewhat, so it becomes a little bit more sinusoidal. If it becomes a little more sinusoidal, it contains less harmonics. So our harmonic content is reduced, and we're now at about 36% THD. And by removing some of the harmonics, we improve the power factor to 0.9. If we look at a multi-pulse drive system, this next example, we're talking about a 12-pulse drive system. There's cancellation of harmonics that's created through phase shifting. This smooths out the current waveform, becomes more sinusoidal. We end up with 5th and 7th, 11th and 13th harmonics. THD in this case is 9.3%, and our power factor has improved to 0.98. The last example is with an input harmonic filter applied to the 6-pulse drive in the first example that did not include a line reactor. So with the input filter, we've reduced the total harmonic current distortion from 73% to 5.8%, so more than a 10 times reduction in the current harmonics. This improves the power factor to 0.99. So we can see from these that the true power factor is determined by the harmonic component of the variable speed drive and not the inductive or capacitive components of the variable speed drive. Those components are essentially unity. So now let's look at how harmonics and power factor can be calculated using computer simulation. This first slide shows simulations done using MIRUS's proprietary software. This software can be used to simulate variable speed drive applications to show how these devices affect current and voltage distortion. The software is free and can be downloaded from our website. It does not compete against EasyPower or other power analysis software because it only analyzes harmonics. But since it only addresses harmonics, it does it very effectively and can be used to generate the load harmonic current spectrums for use within EasyPower. I will discuss this further a little later in the webinar. In this the application shown, we have a utility source of 100 MVA at 13.8 kV, a user transformer at 2 MVA, and 6.5% impedance, which steps down the voltage to 480 volts. And our load is a 500 horsepower PWM variable speed drive loaded at 100%. When we run the analysis, the software will get valuable parameters, power parameter data, voltage distortion, current distortion, total current, and so on, at various points along the one line. So we show them at the distribution panel, we show them at the output of the user transformer, which we define as PCC1, and then at the output of the utility, or at the utility source, which we define as PCC2. But what's important in our analysis today is power factor. And as you can see here, as I zoom in a little bit on this, the displacement power factor in this example is 0.98 lagging. The negative indicates lagging. And our true power factor is only 0.82. We don't show a sign here. Basically, that sign is reflected by the displacement power factor, whether it's lagging or leading. If we run another analysis with a harmonic filter added to the input of the variable speed drive, we can see that the distortion is reduced, our current distortion is reduced down to 6.4%, which also reduces our voltage distortion. And by removing the harmonics, we've now restored our true power factor to near unity, or 0.98. So it's basically now reflected as the same as the displacement power factor on our system. So we can quick and easily see that by removing the harmonics, we're going to restore our power factor to near unity. With the SOLV simulation, we can get full harmonic spectrums for current and voltage at various locations along the one line. This information then can be used for the nonlinear load spectrums required for harmonic simulations using EasyPower. So here we show the analysis done without any harmonic mitigation. This is the current harmonic spectrum shown as a percent of fundamental, also an RMS value, and the phase angle of each of the harmonics. So you can see the predominant harmonics here are fifth at 54%, 270 amps. Seventh is just under 30%, or 147 amps, and so on. With the input filter added to the variable speed drive, our fifth harmonic now is reduced to just 0.66%, and seventh is reduced to 5%, and so on. So there's a substantial reduction in the current harmonics being generated by the nonlinear load. So when using EasyPower to determine power factor under nonlinear loading, we can enter the current harmonic spectrum from SOLV simulation as the load current profile. For this example, we have used the current spectrum when the variable speed drive has no harmonic mitigation applied. So here we have about 56% fifth harmonic, 29, almost 30% seventh, and so on with the phase angles. For our comparison, a second power system model is created using the harmonic current spectrum when a wide spectrum harmonic filter is applied. Then step 3 is to calculate the displacement power factor at each bus using the power flow module. So you can see here when we run this with a pure nonlinear load, the power factor is 0.998, so essentially unity. There is no displacement of the current relative to the voltage. For distortion power factor, the harmonics module is used to calculate current total harmonic distortion. So here with the application without harmonic mitigation, you can see our total harmonic current distortion is 63%. And that has created voltage distortion of nearly 6% on the bus. The harmonic module is also used to calculate current distortion with the harmonic filter applied. And so here we are at 6.38 or 6.4% current harmonics with the filter, and just over 1% voltage distortion that results from that current harmonic. With this information, we can then calculate the distortion power factor, HP PF, and true power factor. So distortion power factor, as we introduced earlier, is equal to 1 over the square root of 1 plus the total harmonic current distortion squared. And then once we've determined the distortion power factor, we can multiply the displacement power factor times the distortion power factor to get our true power factor value. So if we look at the two examples now, actually this is not with a line reactor, this is without any harmonic mitigation treatment. Current distortion is 63%. That results in harmonic distortion power factor of 0.847 and a true power factor of 0.845. With the harmonic filter, with current distortion at 6.4%, the distortion power factor is 0.998. Multiplied by the displacement power factor, we end up with 0.996, or essentially unity power factor. If we compare these values to the values that we saw earlier using SOLV simulation, there's close correlation. The difference is primarily that in the SOLV simulations, the models we are using use real capacitive, inductive, and resistance elements. So the lower power factor reflects the inductive and capacitive components of the filter as well as the harmonic components. So the first misconception is that low power factor is normally caused by electric motors and other inductive loads. The reality is low power factor is most often caused by distortion, reactive power, introduced by harmonic generating power electronic nonlinear loads. So now let's look at how power factor correction capacitors can be used to improve a low displacement power factor. Here we have our power triangle, and we've taken an example where the power factor is 0.8. So our apparent power is 1000 kVA and the real power is 800 kilowatts. In this example, the displacement angle is 36.9% and the reactive power, which is lagging, is 600 kVAR. So if we want to improve the power factor to, say, 0.93, let's say we're a utility where the minimum power factor allowed is 0.9, so we want to raise it to a comfortable level above that. So we choose 0.93. If we choose 0.93 as our power factor, then the apparent power we would need to be at is 860 kVA. We substitute the apparent power and real power into this equation, we can determine what the value of reactance we need to get down to. So at 860 squared minus 800 squared, we're 315 kVAR. Therefore, the amount of capacitance that we need to add is our existing 600 value minus the 315, which is our targeted level, which is 285 kVAR. So if we add 280 kVAR of capacitance to the system, well, it will result in a power factor of 0.93. What happens, though, when the low power factor is due to harmonic kVARs and not inductive kVARs? Power factor correction capacitors, which can be beneficial when applied to inductive loads, such as fixed-speed motors, can make matters worse when applied to nonlinear loads. In this example here, we're showing a distortion harmonic component, which is quite large. There's a lot of harmonics, a lot of reactive powered harmonics, and a relatively small inductive component. And we can see in this scenario, if we try to target the inductive reactive power by applying capacitive reactance in the opposite direction, we will tend to overcompensate because we'll be trying to compensate for a very low power factor that is low because of the distortion component. Power factor in this case must be improved by applying harmonic mitigation equipment. And misapplication of power factor correction capacitors can lead to overcompensation and resonance with the power system. Power system resonance occurs when inductive and capacitive elements have the same impedance value at a harmonic frequency that is present on the power system. So here we have a very simple one-line diagram. We have a nonlinear load, which could be a variable speed drive, which injects harmonics into the power system. We have a transformer that's in series with that variable speed drive, or it could be a reactor in series with that variable speed drive. We have our power system impedance, transformers, utility impedance, and we've connected power factor correction capacitors in parallel to the bus, and we have other loads on the bus which could be fixed speed motors or other inductive type loads. This one-line diagram can be shown as an equivalent diagram as we show here on the right side. So here we have our current source of harmonics injecting harmonics back in the power system. The power system pass through the transformer's impedance, and then they meet this parallel combination of capacitance and inductance. This is the combined reactance of the capacitors and the combined reactance of the system impedance, the load impedance, inductance values, the load inductance values, the power system inductance values. Resonance occurs when these values are equal. We can see that our reactive power inductive curve and our capacitive reactance curve, when they cross, is our resonance point, because that's where the reactance is equal to 0. And so if we have any voltage at that particular frequency, that voltage will drive current and circulate current in that circuit. As current circulates in that circuit, it produces voltage drops and additional voltage distortion at that harmonic number. The additional voltage distortion, voltage value drives more current, and it continues to build. And that's essentially what resonance is. And what controls the resonance or limits the resonance is ultimately the resistance in the power system. But we can reach very high levels of current distortion and voltage distortion at the particular resonant frequency when this occurs. And this can cause many problems, including the destruction of capacitors, fuses, surge suppressors, failure of connected equipment, and ultimately system shutdowns if it gets severe enough. So let's take a look at an application where the addition of power factor correction capacitors made distortion levels much worse. In this case, we have an oil field in Midwest USA that was equipped with electrical submersible pumps. So these pumps push water or whatever, some fluid into the ground to force up the oil when the natural pressure isn't enough to bring the oil to the surface. So there's a lot of these devices that are used in these fields. They run on variable speed drives and they draw a lot of harmonics. So the utility saw that their power factor was low, so they installed power factor correction capacitors, and of course they made the oil company pay for the installation of these power factor correction capacitors. Somewhat later, they discovered that their voltage, the voltage distortion was high, that the site was not meeting IEEE 519 limits, so they had instructed the oil company that they needed to install harmonic mitigation equipment. So as we were doing the analysis of the application, we realized that the levels of voltage distortion relative to current distortion seemed higher than they should have been. And this is based on our experience of doing many such applications. So we convinced the utility to turn off the power factor capacitor banks and monitor the system, and they provided this data back to us. So there were 2 capacitor banks. When they switched one capacitor bank off, the current distortion dropped from 30% to around 20, just less than 20%. And voltage distortion as a result dropped from 14% to 12%. And the power factor actually went up, not down. When they went to no cap banks, the current distortion dropped further, the voltage distortion dropped further. So these power factor correction capacitors were creating a resonance condition. The harmonics were present on the power system because of the electrical submersible pumps, which were variable speed drives. And the resonance was causing an increase in current distortion and in voltage distortion. So we convinced the utility to permanently disconnect their power factor correction capacitors. And the oil company ultimately put in harmonic filters to address the harmonics that was still present on the power system and lowered the voltage distortion levels very comfortably below the 5% required by IEEE 519. So our second misconception is that low power factor can always be corrected by adding capacitance. In reality, if low power factor is due to distortion reactive power, adding power factor correction capacitors will not only be of minimal benefit, they may very likely make the harmonic problem worse by resonating with the power system impedance. In order to discourage customers from operating with a low power factor that poorly utilizes their distribution equipment and increases losses, utilities often charge power factor penalties. If power factor is lower than required by the utility, which is often 0.9 or 0.95, the utility may also apply this power factor penalty. And in this case, we look at an example here. We've got if the minimum power factor required is 0.9, but the actual peak demand is 800 kilowatts and 1,000 kVA. So again, we're back to our earlier example where power factor is 0.8. And utilities will often charge as if, do their demand charge as if the power factor was 0.9 and not 0.8, though they'll calculate it based on a 0.9 power factor on 1,000 kVA, which would be 900 kilowatts. So they'll apply the power penalty demand charge at 900 kilowatts instead of 800 kilowatts, which would be a 100 kilowatt penalty. If the demand charge is something like $10 per kilowatt per month, then that penalty is $1,000 per month, which is very significant. So if we decide we want to improve the power factor to 0.85, so we're not going all the way to 0.9, but we're improving it to 0.85. If we do the calculation now at 0.85, we end up with 800 kilowatts divided by 0.85, or 941 kVA. So now we have 941 kVA instead of our targeted 900 kVA. So we're paying 947 kVA. We're paying a penalty of 47 kilowatts. If we improve the power factor to greater than 0.9, so anywhere between 0.9 and unity, there would be no power factor penalty. And it is important to note that if the low power factor appears only under lightly loaded conditions, it will not affect the demand charge. So if our power factor penalties are only applied as an increase to the demand charge, then having a low power factor under lightly loaded conditions is not a problem. What we need to make sure is that when we're at our demand load level, that our power factor is above the minimum power factor requirement. So our third misconception is that power factor must always remain high to prevent power factor penalties. Power factor penalties are only applied at times of peak demand. Therefore, low power factor that occurs only during light loading conditions would have no consequence. Now let's look at the application of a passive harmonic filter. It can be an excellent choice for improving power factor when reactive power component is predominantly harmonics. But having a properly designed harmonic filter is critical to ensuring that harmonic mitigation meets the targeted levels without introducing excessive capacitive reactance under light loads or under any load condition, but particularly light loads. The large capacitor banks of conventional trap filters and most broadband filters present a high capacitive reactance to the power system, which can raise voltages or cause excitation control problems with generators, and also shows up as very low power factor over a wider load range on the filter. Let's have another look at the SOLV computer simulations that we introduced earlier. Without harmonic mitigation, the displacement power factor is high, but true power factor is low due to the high distortion component. When the harmonics are reduced to 6.4% ITHD by the application of the wide spectrum harmonic filter, true power factor is increased to essentially the same value as the displacement power factor component. One of the best options then for harmonic mitigation is the wide spectrum passive harmonic filter. This example of filter treats the entire spectrum of harmonics generated by the variable speed drives. You can get better than 18 pulse performance or active front end performance, active front end drive performance with the application on a simple 6-pulse VFD. You can guarantee to meet the IEEE 519 harmonic limits of total demand distortion of less than 8% at the input, voltage distortion of less than 5%, or today's 2014 version of IEEE 519 actually relaxes that total harmonic distortion to 8%, but it can guarantee the performance of less than 5. And there are models available that can get current distortion down to less than 5% if that is necessary on applications where the short circuit ratio is less than 20. As we've shown earlier, by removing the harmonics, we can restore the power factor to near unity. We can ensure compatibility with generators by making sure that the capacitive reactance never exceeds 15% of the rated kVA value. They're extremely high efficient devices, and the key is in their reactor design. This slide shows a typical configuration. We've got multiple windings on a common core. We'll have the 3 windings shown here. On the input side, we have a high impedance winding. That is our L1 winding. On the output side, we have a compensating winding, which reduces the voltage drop and improves the performance of the filter. There's a parallel branch connection that is tuned to a specific harmonic, but it provides broadband or wide spectrum reduction of the harmonics, and is designed to ensure that there's very low capacitive reactance. On the input side, we're tuned below the 5th harmonic so that we don't import harmonics from upstream. The harmonics that are present on the power systems in 3-phase applications, probably 5th, 7th, 11th, and 13th, and so on. So we're tuned below that to ensure that they don't get attracted into the filter. And on the output side, we're tuned above the 5th to remove the harmonics generated by the variable speed drive load. So this slide shows a typical reactive power capability curve. All generator manufacturers will be able to supply you with a reactive power capability curve. It shows the kilowatt values on the Y loading on the Y-axis and the kVAR values on the X-axis. On the right side, in this case, we've got lagging reactive power, kVAR. On the left side, we've got leading reactive power, or capacitant power. If the reactive power load that the generator sees falls within this envelope, then the generator will operate without any problems. So as you can see, it can handle a lagging load quite effectively, all the way up to over 80% reactive power. Whereas on the capacitor side, capacitance side, leading side, it can only handle 20% capacitive reactance at no load. So we need to make sure that our filters, when they are applied to the system, fall within this envelope, as is shown here. But many filters, unfortunately, have much higher capacitive reactance, and we're resulting in levels of capacitive reactance that are outside the curve and can cause operational issues with the generators. One of the important design parameters, therefore, for a passive harmonic filter is to have low capacitive reactive power. So here's some measurements taken on a 300 horsepower wide spectrum harmonic filter. This is our reactive power, leading, lagging, and the loading in kilowatts. So we can see at no load conditions, we're at 15% or less. That we are leading at low load conditions, but we're 15% or less, and then it drops, and then at a certain level we end up starting to go lagging, and we'll have reactive power, lagging reactive power as we load up the filter and the drive. Again, many filters will fall into this range here with the capacitive reactance, which, as mentioned earlier, can create issues with generator applications. And if you keep your reactive power low, then you're going to have a much better regulation of power factor on the input of the drive. So here we're showing true power factor, leading on the left side, lagging on the right side, and we can see that 0.95 or better, we're at that level at about 20% loading and above. So we're near unity power factor over a very wide range on the filter. Under light loads, power factor does go leading, but as mentioned earlier, we ensure that our capacitive reactance is very low, so that leading power factor is not going to cause problems with the power system when it's running at these light loaded conditions. So we don't require capacitors to switch out the caps as many other filters would require. So misconception number 4 is that leading power factor is a problem for generators under any loading condition. The reality is, it is true that generators typically handle inductive loads better than capacitive loads. They are capable of handling a leading power factor load provided the capacitive reactance remains within the generator's reactive power capability curve. A harmonic filter with less than 15% maximum capacitive reactance will meet this requirement. And if leading power factor is a concern when using passive harmonic filters, they can be equipped with capacitor switching contactors that operate under lightly loaded conditions. As I mentioned earlier, some harmonic filter designs require contactors because their capacitor reactance is quite high. But when properly designed, they aren't necessary. And in these instances, keeping the capacitors in the circuit under all loading conditions can save cost of the contactor and can also help in protecting the variable speed drive from line side transients. So this slide shows some measurements taken on an offshore drilling rig where there was voltage transients, there was a dip in the voltage and then an overshoot and ringing associated with that. That were the result of DC drives in the phase back angle control of the DC drives in interaction with the system impedance, the generator impedance. So these over voltage conditions were causing the variable speed drives to fail. So we actually applied our filters in this application, not as much to reduce the harmonics that the drive was generating and introducing back into the power system, but rather to protect the drive from these over voltage transients. Because you can see with the filter connected, the over voltages are removed. And we have much cleaner voltage now being applied to the variable speed drive. So there are situations, we also had applications where the over voltage transient was introduced by the utilities power factor correction capacitors. When they switch in their power factor correction capacitors, it causes a dip in the voltage, there's an overshoot and ringing, and the input filter can protect the drive in those cases as well. But you would, if that is the need, then you need to make sure that the capacitors are kept in the circuit under no load conditions. So misconception number 5 is that harmonic filters must always be equipped with contactors to switch out capacitors under light loading conditions. Reality is, a properly designed passive harmonic filter with less than 15% maximum capacitive reactance as a percent of its kVA rating does not require a contactor to switch out capacitors at light loads. In fact, keeping the capacitors in the circuit can help protect the VSD from over voltage transients. And finally, we often hear from customers that they never want to have a leading power factor under any conditions. But the reality is that there are many conditions under which a leading power factor will not cause problems. And in fact, if other loads in the power system are inductive, the introduction of some capacitive reactive power can be a good thing, as it could provide some compensation to improve overall power factor. So we need to be careful of placing conditions that are too rigid with respect to power factor, which can lead to installations that are more complex, costly, and unreliable than is necessary. So in summary then, we know that harmonics generated by nonlinear loads have led to many power factor misconceptions. But in reality, low power factor is often caused by harmonic generating nonlinear loads rather than inductive loads. Power factor correction capacitors are not always the right solution for low power factor, and they can introduce system resonance issues. Power factor must be high during peak demand loading to prevent power factor penalties, but can be low at lighter loading conditions. Properly designed harmonic filters do not need capacitor switching contactors, and providing that reactive power remains within a generator's reactive power capability curve, it is certainly capable of handling a leading power factor load. And low leading power factor is not necessarily a bad thing as long as the capacitor reactance is kept low. So I want to thank you for your attention today. I'll now pass the mic over to our application engineer, Alex Hoevenaars, who's been monitoring the questions, and he's going to bring them forward, and we'll see how many we can answer.
Thanks, Tony. I see a few of the questions were asked early in the presentation, which may have been addressed later on, but I'm going to go through them to address each person's question, perhaps maybe a reinforcement of the concept, or it's maybe very slightly different that it could be good to clarify. The first question is about resonance, and they asked, what are the likely scenarios for resonance for cap bank installation? They mentioned that their facilities are tuned to the 4.7th harmonic, and they want you to elaborate perhaps on why we did tune below the 5th in order to prevent resonance with the 5th.
An excellent question. I do have some slides that I present in other presentations and seminars that I do. But essentially, it's the same reason why our harmonic filter is designed to have resonance below the 5th harmonic. And that is that the harmonics that are currently present on a power system are going to be 5th, 7th, 11th, 13th, and higher harmonics. There are rarely harmonics in the power system below the 5th, although, you know, many of you would say, well, what about the 3rd harmonic? Well, 3rd harmonic is present when there's single phase to neutral loads, and it's a zero sequence harmonic. So in applications where we're at the 480 volt level or 600 volt level, we rarely have single phase loads. So we rarely see 3rd harmonic. If we do see 3rd harmonic, it's zero sequence, so it's not going to be affected by capacitors that are connected phase to phase. So we design below the 5th so that when we connect to the power system is inductive. And the inductance of the power system is going to lower that resonance frequency further. It's going to bring it, if it starts at 4.7, it's going to take it down even lower if you have an inductance in the power system. If you're going lower, you're moving away from the harmonics that are present. If you are tuned above the 5th harmonic, say above the 7th harmonic, and you add the power system inductance, your resonance frequency now, combined resonance frequency now is going to move down, and it could move to the 7th harmonic and create a resonance with the harmonics that are present on the power system. So an excellent question, and it makes a lot of sense. If you are putting in capacitors to deal with the displacement power factor, you do want to consider detuning those capacitors to a harmonic number that's below the 5th.
Okay. The question is about utilities penalties. Do they penalize for leading as well as lagging power factor?
Yeah, typically the utilities will penalize based on a minimum power factor, regardless of whether that power factor is leading or lagging.
Perhaps we should clarify that it happens at the peak. So if you're leading but under low load conditions, you wouldn't get penalized. Nor most utilities wouldn't penalize you for being leading in a very low load condition.
That's right.
So the question is about surge suppression. Can harmonics damage surge suppression devices, and how do we diagnose and fix that issue?
Absolutely, harmonics can damage surge suppression devices, and actually surge suppression devices can resonate with harmonics on the power system. They often have capacitive elements in them. So it is something that you do need to concern yourself. I'm not an SPD expert, and there are many different types. So I think it's best to address those issues with the suppliers of surge suppression devices.
Okay, the next question, it relates to EasyPower. How we can, if they use a current injection model to model the harmonics, and we have the requirements to enter them as current injection, how do we enter it if we don't have any phase angle? Is there a way to properly model the harmonics if we don't know the angle of phases?
Okay, I'm not exactly sure. I know that there are some people from EasyPower that are participating. I'm not sure if they want to come in to answer that question, or if we will have to divert that to a later answer. What I do know is that if you use the SOLV computer simulation to generate the current spectrums, it will provide phase angles. So you'll get both the amplitude and the phase angle of the harmonic.
And then using that, you can enter that into EasyPower to get the current injection you need.
There also is, I believe, there's libraries within EasyPower of some nonlinear loads, and those libraries likely contain both the magnitude and phase angle.
Okay, someone else is asking about TDD. Why haven't we seen the term TDD in your presentation? What is TDD, and is it equal to THD?
All right, excellent question. I don't know that I guess I didn't refer to it in this particular webinar, but TDD is a definition that was a term that was created for IEEE 519, and TDD is defined as the total harmonic distortion, or THD, times the ratio of the actual fundamental current measured divided by the peak demand fundamental current. So in most of our applications, we will say that the peak demand current is going to be your full load current. So if you get a variable speed drive and you're putting a filter on it, the full load current of that variable speed drive is going to be your peak demand current. If you're measuring at, say, 50% load, and your fundamental current is then at 50%, the ratio of measured current to peak demand current now is 50%. So TDD is actually going to be 50% of your THD value. So if your THD value is 10%, TDD is 5%. And essentially, TDD rightfully allows for higher THD values under lighter loaded conditions when the amount of actual current harmonic being injected in the power system is lower. So a higher percent of a light load is going to be less harmonics than a lower percent of a heavier load. So that is the rationale for TDD, and it makes sense. I hope that answers your question.
We have a few questions all around the same topic, so I'll just kind of group them into one, asking about efficiencies of our filter and of passive filters in general, how efficient they are, and how that would affect the overall efficiency of the system.
Okay, there are some variances in the efficiency of different types of filters. I can tell you that our input filter is greater than 99% efficient, so there's only 1% losses introduced by the filter. The larger filters are actually much better than that even, so you get to like 0.5% in losses. So we introduce very low losses into the system. Certainly the losses of the filter are much less than the losses of the variable speed drive that they're being applied to. I can also say that the combination of an input filter and variable speed drive, the total losses of that, a 6-pulse drive and an input filter, are much less than the alternative solutions for low harmonic drives. So if you have a multi-pulse drive system where you're doing phase shifting to reduce the harmonics, you've got the added losses of the transformer, which are much more significant than the losses of the filter. For active front-end drives, which are defined as low harmonic, and although I have another presentation that discusses active versus active harmonic mitigation techniques, but active front-end drives in it are much higher losses. So also introduce the heavier losses and are much less efficient than the other solution. So yes, it does introduce some losses. We also have found in many applications where the application of the filter improves the operation of the drive and whatever it's supplying, be it a pump or a fan or so on. So the net, ends up being a net reduction in power consumption with the use of the filter, and it's because it increases the DC bus voltage and actually improves the operation of the drive.
Okay, a quick question that I see saying, please list the IEEE standard number dealing with the filters. That's IEEE 519. That deals with harmonics and all the issues associated with it. The next question is, how do harmonics produce heat if they produce no usable work?
Okay, so this is an excellent question in that many people mistake the current reduction when you're applying, say, power factor correction, or in our case, removing the harmonic currents. They equate the current reduction as a reduction in real power. Actually, what it is a reduction in reactive power, and so reactive power does not do any useful work. However, this current flows through the power system, and as it flows through the power system, it introduces losses. It introduces losses in the cables, it introduces losses in the transformers, and those are the real power. That's the real power losses. That's what the utilities are concerned with when they demand power factor, or they apply power factor penalties. Because these losses, these additional losses can be very significant to the utility, and also they have to increase the capacity of their system in order to deal with the reactive power. So yes, it doesn't do any useful work, but the currents create real watt losses in the system.
Okay, the next question is, relates to thyristor-controlled power systems. And they're asking if the leading power factor is of a special concern or more concern in a thyristor-controlled power system rather than just a diode bridge.
Okay, so thyristor rectifiers control the firing of the for the diode bridge. So they're going to, if they're trying to control the DC bus voltage level, and to lower the DC bus voltage level, they'll delay the firing of the thyristor. And so the voltage won't be present and it won't switch to the other phases when it would normally switch. That delay in the firing introduces a displacement power factor. The current ends up lagging the voltage. So you end up with a drop in displacement power factor. It's always lagging. It's always going to be a reduction in displacement power factor that's lagging. So if you have capacitors in the system, in that scenario, additional capacitance in the system will help somewhat to offset that lagging displacement power factor that's introduced by the thyristor bridge.
Okay, I got a few questions here I'm seeing about active solutions, either active front ends or parallel active filters. I know that wasn't necessarily the content specific to today's presentation. We do have other, Tony might reference another webinar we do on that. But they're asking about, one person's asking about taking into consideration, what do you take into consideration when sizing a filter for drives with active front ends, and also then someone else is asking you about parallel active filters and application questions associated with that.
Okay, yes, so the topic of comparing a good passive solution to an active solution, the various types of active solutions, active front end, parallel active filters, and so on, is a very complex topic, not something that can be answered, quickly to one question. But we do have a webinar that's actually recorded and can be found on our website if you're interested in doing it, and we will probably run that webinar again in a few months or so. We just did one recently. But what happens with active front ends is the active front end has an IGBT input bridge instead of a simple rectifier input bridge. Those IGBTs switch, and when they switch, they introduce switching harmonics. And these switching harmonics are high frequency, and they inject these harmonics back into the power system. The active front end drive needs to have a passive filter, an LCL. They call it an LCL passive filter that needs to be built into the active front end drive. You have to be careful about filtering an active front end drive with another filter, because it already has a filter built into it, and you can create problems. So we don't normally recommend it. We wouldn't have a device that could be applied to an active front end drive. What we recommend is when your requirement is simply low harmonics, there's no reason to put in an active front end drive. You're much better off to put in a simple 6-pulse drive and a good input filter. You're going to have a passive filter anyways. Even with the active front end drive, you're going to have an LCL filter. And actually those LCL filters are more likely to resonate with the power system than the input filter for a 6-pulse drive. So rather than try to consider how to filter, additionally filter an active front end drive, I would caution you or advise you to use a 6-pulse drive with a proper input filter.
Okay, let's see another question about monitoring. Do modern meters and power quality meters, do they measure total power factor, or do they just measure distortion power factor? How can you get a meter that will monitor the true power factor in order to properly include the harmonics?
So all of the utilities are looking into smart grid, and those smart grid applications require new digital meters. All of those meters will measure displacement power factor and true power factor, and therefore distortion power factor as well, or they'll show distortion power factor as well. So most good, certainly digital meters today will measure. So the newer meters that the utilities are using do measure displacement and total power factor, and true power factor. There might be some applications where there might be an analog meter that doesn't, but I know in general most of them do now.
I think that's, I'm just scrolling through the last. Yes, the slides will be available. There's a bunch of people asking about whether the slides will be available. The slides definitely will be made available for everyone, and the recording will also be available. I think that answers. Sorry if anyone's question wasn't answered. Feel free to email us at mirusinternational.com. We can hopefully answer any of those questions that we missed here.
I do believe we'll also get a copy of all of the questions. EasyPower will forward them to us, and we'll also address any that were missed. We can provide answers separately. So I think that does it for us today. Once again, I want to thank you all for attending the webinar. I hope that you found the information informative, and I look forward to providing other sessions maybe in the future on other topics. So thanks once again. Thank you very much.